Hello everyone, welcome to the first lecture of the Early Earth series that I wish to make in order to give you all a brief understanding of the Early Earth regime. So before we go ahead, I just thought it's good to give you all an introduction, just to get you familiarized with all the terminologies, what are we exactly dealing with, what do we currently know about it, the controversies, all of these stuff, before we get into the intricacies. So let's get started. So firstly, we need to understand what exactly constitutes the early Earth. So we can take the entire history of the Earth as these eons, which is the broadest classification of the timescale, and we can see that from time frame from 4.5, which is approximately the age of the Earth, giganum, to around 2.5. That is what is constituting, or what we can classify as the early Earth, majorly. So we understand that if you take the entire history of the Earth, we notice that the Archean Earth corresponds to around 33% of the entire Earth's history, and the Hadean corresponds to 13%. So we can see that around 50% of the entire Earth's history is constituted by its early phase. So understanding the early Earth is key in order to understand our planet as a whole. So going ahead. So what all challenges do we have when we go about understanding the early Earth? How much do we know? That is what we intend to discuss right now. So we can notice that unlike the modern Earth, understanding the early Earth can have its own challenges, because the major thing is we don't have that many samples. As the planet as a whole is active, tectonically active, most of the rock units from that time has been lost totally to the interior of the Earth. So we have only a little record preserved. We're older than 3.8 gigaannum, we have not much data as far as the rock record is concerned. So that is a major problem. And the other problem is the Archean rocks. They are extensive, unlike the Hadean rocks. But the problem is they have undergone multiple deformation events. Therefore, the original chemistry of these rocks and the original nature of these rocks as such has been tampered with. So in order to understand what these rocks really were like, we need to call for patient fieldwork and also very thoughtful geochemical studies, because we need to take into consideration all of these chemical changes that might have taken place because of the weathering, intense weathering that it has undergone, and also the severe deformation that it has gone through. Now, coming to the Hadean Earth. As I mentioned, because since we don't have that much samples, the major challenge is that we have to work with just the limited amount of samples that we have in order to get an understanding of what that phase of our Earth's history was like. Yeah, to be really specific, we just have one grain to deal with as far as the Hadean Earth is concerned, because all of those oldest rocks have been lost to weathering, so only the zircons, which are very robust in the case of very resistant to weathering, so they stay. So Hadean zircons that are trapped or preserved in younger Archean sediments, that's the only way we have, only window into Hadean Earth. So that is why the knowledge base of Hadean Earth is also very thin. Moving on. Since we know for a fact that these samples are very low in number, we have to think of other techniques in order to get a better understanding of the Hadean Earth. So interestingly, modern isotopic studies do show that the mantle has a memory, in the sense, whatever processes that happened back then, the mantle is able to chemically, keep a record of those, and that will be preserved there and found in later rocks. So tapping into this mantle memory can give us insights into the Hadean Earth. So since we know that the samples are very low in number, such indirect techniques will be the future of early Earth research. So coming to the Archean Earth, unlike the Hadean Earth, as I previously mentioned, the Archean record is more expansive. But the major challenge is it is difficult for us to find comparable modern counterparts, because we know for a fact that the mantle was hotter back then, so things were slightly different back then, so there are certain rock suites that were restricted to that time frame. So the fact that we can't have modern counterparts is a very big challenge when it comes to interpreting that time frame or the processes that happened during that time frame. And one famous example are cometites, which are understood to have been mantle melts of that time. How do we understand the Archean Earth? Based on what is preserved, we have two types of Archean crust. The first is Archean greenstone belts. Most of our understanding of the early Earth mantle comes from the study of these greenstone belts. These rocks are our windows into the Archean mantle, because they are, as I previously mentioned, rocks like cometites. They are direct mantle melts, so give us a direct insight into what the Archean mantle was like. And the isotopic studies of such rocks is given rise to a lot of interesting ideas, which we will be discussing in the upcoming videos. Now, the second type of Archean crust is Archean granite gneiss terranes. So in the previous case, it is mostly mafic and ultramafic. So we have these greenstone belt basalts and ultramafic lavas that are preserved in the greenstone belts. But when it comes to these granite gneiss terranes, we're dealing with more felsic character. So they are largely compositionally variable, but these terranes generally contain the tonalite, trangimite, granodiorite suite, that is known as the TTGs. So these are windows into our understanding of what was the early continental crust like. What was the first continental crust like? We can do those kind of studies from these kind of terrains. Because TTGs are regarded as the first, how the continental crustal growth happened is primarily through the production of TTGs. So coming to that, a lot of controversies and debates exist on how exactly this continental crustal growth happened. Because there are various tectonic models. People believe that modern subduction, like what we have right now, was not happening at that time. But other people believe that it was the same process all along. So there are still debates going on about that, and we will be discussing more on that in the upcoming videos. Now, coming to the distribution, as I mentioned, we here in this map, we can take a look at the Archean cratons. And these black regions here, we can notice that these are the Archean cratons. And if you notice, I have demarcated these red circles. These are the regions where the oldest rocks are found. And we'll be discussing that in more detail later in this video. So, the major regions, as far as we understand, where the oldest rocks are concerned, oldest rocks are preserved, is in northwestern Canada. We have the Slave Craton. There we have a preservation, and then we have in West Greenland another oldest terrain that has been a subject of a lot of research. And then we have the Pilbara crater in Western Australia. There also we get access to a lot of old rocks. The oldest terrestrial materials could be found there. So these three areas are majorly studied in order to get a better understanding of the early Earth. So coming to the oldest rocks, as I told, we'll get into the detail of each of these three major regions. So the first one is West Greenland. There we have the Isua Greenstone Belt. This has been an area of major research, and it contains records of Earth's earliest mafic magnetism. But interestingly, we don't see much of felsic activity going on there as far as that particular greenstone belt is concerned. So in the sequence, the existence of a continental crust is missing. But further close to that region, we have the Itzhak gneisses. That was firstly studied in order to get an understanding of the very ancient crust, because they were felsic in nature, those gneisses. So that gave us the first clues about what the ancient crust must have looked like. Now coming to northwestern Canada, which is the second region where these old rocks are found, we have the Augusta gneisses. The studies of zircons from these samples indicates that it is at least 4 gigaannum old. We are dealing with really old rocks here. So the Augusta gneisses, became a subject of controversy. That is because the isotopic studies that were conducted on these rocks indicated that the epsilon neodymium values were largely variable. So the study that was conducted by Bowring and Hausch, they suggested that it is indicative of an early Earth differentiation event and a formation of a very early continental crust. But these kind of interpretations were challenged by Moberth et al. In 1997. So the debate whether early continental crust formation happened, or whether we're dealing with a progressive growth, or whether we're dealing with a very early extraction, these are live debate questions. And we'll be dealing with more such questions in the upcoming videos. We'll be explaining and exploring those topics. Now, the third region of interest, as far as the oldest rocks are concerned, is in Western Australia, and the famous Jack Hill zircons, which is having an age of 4.4 gigaannum. These zircons gave us a lot of insights into the early Earth. And here we can take a deeper look into some of the zircons here. So in this particular zircon grain from the Jack Hills, we can see that the single zircon grain has preserved 3 different ages corresponding to 3 different thermal events. So this is interesting because it gives us the idea, or it implies, that the crust at that time was thick enough for metamorphism to take place, so that these three different events were recorded in the same grain. But as I told, we only have, as far as the Hadean zircons are concerned, we just have them preserved in the younger Archean sediments. We don't have the original Hadean rock from which these zircons came from. So the composition of these, so the rocks which hosted these zircons, that is debatable. But based on the trace element chemistry and inclusion studies of the zircons, people believe that it came from a granitic crust. Now, focusing more on the controversies, as I mentioned all along, it seems like, what is the nature of the first continental crust, whether it was felsic, mafic? These are poorly understood because we don't have direct access. All we have are zircons. But given the fact that we have zircons that are this old, indicates that the first crust is probably felsic. But again, the exact composition, whether it was tonalitic or whether it was granitic, that is again a subject of debate. So yeah, there are many examples of conflicting interpretations, but these controversies are important because they challenge our status quo. We are able to reinterpret the data and entertain all kinds of ideas. So we are more and more closer to reality only when we have controversies. So that's a good thing in that manner. So in order to, since our own record is this low, we can look onto other terrestrial planets to get an idea of what might be the nature of the first crust. But the problem is, it's a paradox, because all of the other terrestrial planets indicate that the first crust was mafic, but yet we have the oldest zircons on Earth that are believed to have come from felsic rocks. So it seems like the Earth's history is not exactly comparable to the other terrestrial planets in that sense. So the origin of the Earth's first continental crust and the composition of that crust, the mechanism by which it grew, these are all important open questions that could be explored further. So now coming to, when we think about early Earth research, it is important to understand whether our assumptions are correct. So when we talk about early Earth, can we apply the same principles that we hold right now to the early Earth? People believe that there are certain processes that happened back then which are not applicable to the present modern Earth. So processes like impacting accretion that happened in the very early stage of the Earth's formation, these things are not applicable to the modern Earth. So they obviously cannot be part of the uniformitarian thinking. And we also have on top of that rocks that are restricted to certain eons, like comatiites, which are largely restricted to the Archean. So it does indicate that the processes or the conditions were different back then. So it seems like we need to take into consideration these things, but nonetheless, recent studies are indicating that the early rocks did form through modern processes. So I believe, it seems that a uniformitarian approach is valid, as long as we understand what exactly were different back then. And if we take that into the consideration, I believe a uniformitarian approach is feasible in order to understand the early Earth. Of course, there are debates. People still debate about whether this approach is valid or whether a non-uniformitarian approach is more valid. So we'll be dealing with all of those such questions in the upcoming videos. So as far as the next video is concerned, we'll delve more into the early Earth mantle. We'll take a look at its isotopic composition, what were the major insights we drew from such studies, and what all we can understand about early planetary processes from such isotopic studies. So that's it as far as this video is concerned. So I'll see you in the next one. Till then, take care.